Hello again, everybody. Welcome back to a new screencast lecture. Today we're going to talk about weathering, erosion, and deposition. Let's get started. First, we need to know what sediments are. Sediments are small pieces of rock and mineral. You may have heard of the term sedimentary rock. Well, sedimentary rock is made up of small pieces of rock, and those small pieces of rock can vary in size, and they are classified by the size that they are. So here you see the different sizes of sediments going from smallest to larger in this case. And these are the three that I would want you to know. The smallest is clay, then comes silt, and then comes sand. I would not expect you to know the sizes of them, but just know that clay, silt, sand in that relative order for size. Here's a clip. It's called Water Retention of Soil from the YouTube channel Teaching Bio Project.
Now what I have here are three measuring cylinders, 100 milliliter each, three funnels with filter paper and soil specimens. Let me just show you how one should same amount of soil in each of the funnels. I took 3 big scoops of soil. Of course, if you want to have exact measurements, you should weigh the soils to have the same amount of soil. And then I pour 100 milliliters of water into each funnel. This is the loam, the garden soil, and you can see the water has already started to drip through. The more clay soil, and the sand. Right, now this is going to take a while, so let's have a look at the samples that I did earlier this morning. Right, number 1, sand. Remember, it had 100 milliliters of water poured into the funnel. Number 2, loam. And number 3, clay. Perfect. Can you see that the sand let through most of the water, very low water holding capacity? About 42 of the 100 milliliters, and loam in the middle. And look at the color of the water that ran through the loam, dissolved salt, which also tells you and gives you an idea that this type of soil contains a lot of nutrients. So by comparing the amount of water that ran through, we can determine and compare the water retention capacity of different soil types.
That's a pretty good video, and you can see that the clay does not allow water to percolate through it very quickly or very easily at all. The soil around here is mostly clay. That's one of the reasons why after a big heavy rainstorm, a lot of times it takes quite a while for that water to dissipate and for the soil to dry out. On a related case, let's take a look at this next video clip. It's called Water Movement in Soil.
When rainfall hits the Earth's surface, one of two things can happen. Water can run off the land, or often, with the help of sound land management practices, water can move into the soil to be an environmental positive rather than a negative. The soil itself has an influence on whether water runs off or moves into the soil. Here's a brief explanation of how and why soils transmit water at different rates, and why you should check a soil survey when you're concerned about runoff, flooding, leaching, or other environmental hazards. Water movement in the soil is strongly influenced by soil particle size, or texture, as well as structure and pore size. Soil texture is the relative amount of sand, silt, and clay-sized soil particles. Sand particles are the largest, silt is intermediate, and clay is the smallest. Water moves more quickly through the large open macropores found in sandy soils than the smaller pores of silt, or the much smaller flat-shaped micropores in dense clay soils. Soil structure also impacts water movement. Water moves more quickly downward in soils with granular structure than a soil with platy structure that forces a longer indirect path downward. Other structures include prismatic and subangular blocking. Water is nearly always moving in the soil, and it can be in any direction simultaneously. Gravity is the dominant force that moves water downward. Restricted soil layers of compacted soil or bedrock are among the reasons water moves laterally. Capillary action, the attraction of water into soil pores, can move water in any direction. Gravity is the primary water-moving force in saturated soils, while capillary actions are the primary forces in unsaturated soils. Capillary force is greatest in soils with small pores. Water moves more slowly through these soils. Well, that's a brief explanation of what a soil scientist calls saturated hydraulic conductivity. In simpler terms, the capacity of a soil to transmit water. Since downward moving water carries nutrients and can carry contaminants into underlying groundwater, soil percolation rates are important in choosing sites for septic fields, landfills, and other waste burials, as well as underground storage tanks and other uses.
That's a really well-made video. I hope you paid attention to the part where they talked about how water moves through the soil. I thought they did a really nice job of showing that. Water movement through the soil is very, very important. So water gets to plants and the plant roots. You want the water to travel through pretty quickly, but you don't want it to go through too quickly that the water doesn't have time for the plant to get all the water that it needs, and then the soil could dry out very quickly. Or you don't want it to be too slow to penetrate through, where the water stays in the ground and makes the plants more susceptible to rot or diseases. So you want a nice balance. So you don't want too much sand where the water is going to go through too fast and dry out the soil. You don't want too much clay where the water doesn't travel through, and then the plants will have too much water sitting there. And then, of course, it depends on what kind of plants you're trying to grow. How are sediments made? So these little pieces of rock, how are they made? Well, that process is known as weathering. And weathering is defined as destructive forces that change rocks into these smaller pieces, or these sediments. There's different kinds of weathering. Let's take a look at different examples of weathering. First of all, there's what's known as physical, sometimes known as mechanical weathering. So there's two different types of weathering. One is physical weathering, and the other one's chemical weathering. We'll get to that one later. Some examples of physical or mechanical weathering. Our first example is wind, and wind damage could look something like this. So what happens is, as the wind blows against the rocks, often it's going to pick up sand, and that sand is going to smack into the side of the rocks and start wearing that bigger rock away. Here's a clip showing how powerful that sand can be. Yeah, that's really neat. I like to see how you can see the sand blowing out at really high pressure, and that is able to scrape off the old paint and rust and the dirt and the grime, and you can see the bare metal back. Almost looks like it's brand new. That's pretty awesome. Wind damaged rocks. Rocks are worn away by abrasion, so that when that form of weathering, that damage is known as abrasion. What I think is really neat is you see a rock like this, and the way this is formed is that the wind is going to pick up sand and it's going to hit the rock. Well, the sand has mass and has weight, and so the wind can't pick it up super high, so more sand stays closer to the ground, and so the bottom of this rock formation gets worn down more at the bottom than it does at the top, because there's more sand causing more abrasion to the rock. So at one point this rock was full. It didn't always look like this, and then the bottom of it has been worn down by abrasion, by that wind with sand hitting the sides of the rock. Pretty neat. I believe these are called hoodoos, and this is pretty neat. Here you can see it again. This looks like a giant rock on a little pedestal. Eventually this rock the same kind of thing is going to happen, where the bottom is going to be worn out more than the top. Here's another example. Here's a video clip showing what happens when people don't respect our natural world and break these hoodoos. It's really kind of sad. This is a good learning lesson for you, not to do this kind of thing.
Guys, starting with the Boy Scouts, thanks to these knuckleheads. That's a Boy Scout leader proudly destroying an ancient rock formation in a state park in Utah, which took 170 million years to take shape. Yeah, I'd say he's probably violating the scout credo of leave no trace. Despite claiming the rock was unstable to begin with, the men could still face charges.
We have now modified Goblin Valley.
No word if they'll also be losing their merit pay.
Yeah, that's kind of a shame, and yeah, they did get themselves into trouble for that. So don't do that at home, kids. Our next example of physical weathering is water. Water smashing into rocks can cause quite a bit of damage on the rocks, so water damage. And here's a video just showing how powerful these moving water could be. So this is called Wipeout by Waves.
Commit to something!
Very, very powerful. This next clip is going to show what water can do to soil and surrounding areas over time. Yeah, you're able to see the sides of that little creek or whatever just being broken down by the moving water. And what another neat thing about moving water is over time, you probably have noticed that creek rocks are mostly rounded. So that over time, these rocks that are jagged and sharp like this will get smoothed down and be nice and round. Those are great for throwing stones and skipping stones. Our next example of physical weathering is known as temperature changes. Changes in temperature can cause damage to rocks. The big reason is that water does something really strange. It actually will expand. In other words, its volume will increase as it goes from liquid water to solid or frozen water. The water will expand. That's extraordinarily unusual. So what you're going to have here is if water gets into a crack and then it freezes, the water will expand and become ice, and it'll start pushing the rocks apart and start cracking and breaking the rock. That is called frost wedging, and it makes a bigger crack. And then that bigger crack, water can fall into that bigger crack, refreeze, get bigger again, and it's just a big process that can keep happening and making the crack and the holes worse and worse. Here's a video. It's called Power of Freezing Water. So you filled the water bottle completely full, all the way to the rim with liquid water. The liquid water froze, expanded, and pushed the cap up and off. Also was able to break the bottle itself as well. Okay, we're done with mechanical weathering. Now let's take a look at chemical weathering. An example of chemical weathering would be acid water. You may have heard of things like acid rain. When water reacts with carbon dioxide, it can make carbonic acid. When water it reacts with sulfur, you can make sulfuric acid or acid rain. This is a video clip that shows a model of how stalactites form. So you know about stalactites. Those are the rock formations that hang from the top of the ceilings of caves. Stalagmites grow from bottom to top. Stalactites grow from top to bottom.
This with water. Add salt, water, and mix well. Add the salt till it does not dissolve anymore. In this way, you will have a solution that is saturated with salt, NaCl. Dip the ends of the rope in the two saturated solutions. Due to capillarity, the water will climb up the rope and collect at the center, and it will drip. Each drop will leave behind some salt on the rope, and this will slowly accumulate. In the caves, a similar process occurs. The water percolates from the wall and drips from the vaulted roof, depositing the minerals it contains, especially calcium carbonate. Stalactites form in this way. After about 1 week, the salt stalactite will have grown a few centimeters.
That was really cool. You saw how these salt crystals can form out of solution, and that is a similar process to how these rock formations are formed. Another example of chemical weathering would be iron rusting. Here's a clip showing iron rusting. So you have a piece of iron here, and this is in a solution. So right before your eyes, you see that rust can happen pretty fast if you have it in a saltwater solution, and especially if you can run electricity through it, that can promote rusting as well. Pretty neat. Another example of chemical weathering would be organisms such as bacteria and fungi can cause chemical weathering. Here's a clip showing biological weathering. What is biological weathering? How do plants assist in biological weathering? When plants cause mechanical weathering, their roots grow into rocks and crack them. When plants cause chemical weathering, their roots release acid or other chemicals onto rocks, which then forms cracks and breaks apart. For example, lichen eat away the surface of the rocks, thus leading to the molecular breakdown of the rocks. And the decaying remains of dead plants and soil tends to form organic acids, which when dissolved in water, causes chemical weathering. Ants, earthworms, and burrowing animals such as rats and rabbits loosen the soil and make tunnels and thus cause weathering of rocks as well. All of these activities contribute to biological weathering of rocks. Well, that's all the time we have for today, so be sure to give us a thumbs up if you liked it, give us a thumbs down if you didn't like it, and be sure to subscribe and comment down below, and we'll catch you next time. See ya!